Hey, geometry students. In this lesson, we're going to be taking another look at circles, and specifically, we're going to talk about figures that you can draw on or around a circle, near a circle. And these would be chords, secants, and tangents. Let's get started. We've already talked about a chord on a circle. It's a line segment whose endpoints lie on the circle. So remember, a circle defined is just you take a center point. All circles have a center, and then we define the circle as all points that are equidistant from that center. The center is not a part of the circle. Other than that, we define it from the center. But the center point does not actually lie on the circle. And then all of those points that are equidistant from the center that make up the circle, if you draw a segment from one of those points to another point on the circle, that would be a chord. A diameter is a special chord on a circle. And every circle has an infinite number of diameters that can be drawn. You can just rotate that thing anywhere within the 360 degrees of the circle, as long as the diameter passes through the center of the circle. It's a diameter. So that's what a diameter is, a special chord, and now you know what a chord is. A secant is similar to a chord, except it just keeps on keeping on. The secant of a circle is a line that intersects the circle at 2 points. So a secant contains a chord, but it's bigger than the chord because it's a line. It continues past the circle on both sides. We say it's a secant line, not just a segment. Okay, so a chord is a segment. A secant is a line. And then a tangent is a line that, similarly to a secant, it's going to intersect the circle, except it intersects it at exactly 1 point. How do we do that? Like, how do we make a line intersect the circle at just 1 point? Well, it just barely touches the edge of our circle. So if I were to try to draw, if I drew a secant line, okay, so keep in mind, a secant line could contain a diameter. I want you to picture a secant line that contains a diameter of a circle. Then we start sliding our secant line toward the edge of the circle. It no longer contains the diameter. Now it just contains a chord. We're sliding it further and further toward the edge. So it's containing a shorter and shorter and shorter chord segment until it gets shorter and shorter and shorter until we just barely reach the edge of the circle. When that secant line gets so small that all of a sudden that line just barely kisses the edge of the circle, and there's just a single point at which it intersects the circle. Now we no longer have a secant, we have a tangent that just barely touches the edge of the circle at 1 point. That point, by the way, is called the point of tangency, point at which a tangent line intersects a circle. So secant and tangent are similar to one another in that they refer to a line, not just a segment. A chord is a segment. Okay, so kind of keep those in mind. We're going to talk about some theorems. These are not obvious theorems. These are really deep, good, useful theorems related to circles. First of all, if a diameter is perpendicular to a chord, okay, so we have a chord that connects two endpoints of that are on the circle. If the diameter is perpendicular to that chord, keep in mind the diameter has to pass through the center. It's a chord that passes through the center of the circle. If that diameter is perpendicular to a chord, then that means that that chord is bisected. It's cut exactly in half by the diameter. We're going to see some examples of this. If you can't picture this, if you're having a hard time picturing this, draw it out. See what happens when you actually draw a real circle and then bisect it with a chord. You'll see that, yes, in order for a chord to, if you draw any diameter perpendicular to a chord, the chord is always cut in half. And it just has to do with the geometry of the center of the circle. A line that passes through the center of the circle is going to pass through the center of any chord that it's perpendicular to. All right, moving on. If a diameter bisects a chord other than another diameter, then it is perpendicular to the chord. Now, this is almost the converse of the first one, but it's not a true converse because of that extra statement. And let's talk about that extra statement at the beginning of Theorem 43.2. What about another diameter? Well, okay, so here's the thing. All diameters pass through the center point of the circle as part of their definition. And because they pass through the center of the circle, and they are chords that connect two opposite sides of the circle, then what ends up happening is, because they all pass through the same center, they all bisect each other. So you could have a diameter and then a diameter that's a few degrees different from the first one. Like there's like an angle between them. It's not a very big angle. Then they will bisect each other because they both pass through the center of the circle, and that's the center of the segment, right? But so what we're saying is we're limiting our discussion to chords that are not diameters. If a diameter bisects a chord other than another diameter, so we're bisecting just a chord that's on the circle or cutting it into two equal parts, they have to be perpendicular for that to happen. So the first statement's converse almost works, except if I were just to write out the true converse of theorem 43.1, if a diameter bisects a chord and its arcs, then it is perpendicular to the chord. There's a counterexample, and the counterexample is another diameter that gets bisected. The point there is that because there's a counterexample, we have to come up with an entirely new theorem. We can't just say the converse of the first is true. Next, the perpendicular bisector of a chord contains the center of the circle. And again, what we're saying there is the perpendicular bisector of a chord. That's what we just talked about in theorem 43.1. It has to be a diameter, and the diameter always contains the center of the circle. So 43.3 is really just another way of saying what we've already said. The perpendicular bisector of a chord is a diameter, and therefore it contains the center of a circle. All right, and then our last theorem. If in a circle or congruent circles, chords that are equidistant from the center are congruent. So chords that are the same distance from the center, even if they're pointing in different directions or diagonal compared to each other, if they're equidistant from the center of the circle, they have to have the same measure. They're congruent. And the same thing, but just flipped around. So this would be a converse statement. Congruent chords are equidistant from the center of the circle. Okay, so we're going to work with these in the next video as we work some problems related to chords, secants, and tangents. A lot of these are just going to be identifying, but we are going to have some math that we can do with these, noting that some things are congruent and some things are related to each other based on where they are on the circle. All right, so watch the video because we are going to be working with all of these terms and making them much more concrete as we look at actual examples of chords, secants, and tangents.